So, you saw this already, okay, and what I was talking about. In this you can see there is one hinge, okay. Clearly you can see this is lead lag hinge, okay. It allows you your blade to rotate in plane easily. It does not have a flapping hinge, but then the blade is still, because of its flexibility, it can bend like this. This idea of this hinge, putting this kind of flapping hinge and lead lag hinge, was actually proposed by a aviation pioneer. His name was Juan La Cierva in 1933 or something. So, this is the time when people were really struggling. They were trying to come up with designs for helicopters, so that you can fly vertically upwards. Okay, aircrafts were already flying since 1902, okay, when Wright brothers invented the airplane, but then a lot of people were trying very hard, and actually it is quite interesting to look in retrospect. At one point Wright brothers, they said that helicopters are too complicated a vehicle to ever fly. Okay, one of the Wright brothers, he had made this statement. Okay, there is people who are working in that, they are actually just wasting their time. Okay, the helicopters can never fly. And in reality, I mean, if you see a helicopter, I mean, from up close, big helicopter, it is still very difficult to really, I mean, believe that it is going to fly actually. Okay, but they are amazing machines, and they are very unique in several ways. So this particular invention of putting hinges was that of Juan La Cierva, and also this force plate. The idea of this, having this one part stationary, other part spinning, to transform motion from the fixed frame to rotating frame using force plate, was also proposed by Cierva. Okay, Cierva was actually an aviation pioneer. He was building a flying car for everybody at that point of time in 1930s. He had made this auto gyro. Remember the picture of the auto gyro which was there in the earlier. Okay. So, he has made that, and he was claiming that it can be used by everybody to commute to their office. They had even shot a commercial way back in 1930s, but then that Great Depression happened in US, and then unfortunately Cierva died in a plane crash, and with him the dream also went away. Otherwise, I mean, things could have been very different, because he was a very, I mean, a genius engineer basically. Came up with, so the idea of this putting these hinges was because whoever was trying to make a helicopter at that point of time, they were experiencing one common problem. The moment you would try to take off with the helicopter, it would actually topple, roll over. The reason was that you saw, we talked about dissymmetry of lift. Okay, when your helicopter is moving in plane, you have higher lift, on the other side you have lower lift. When the hinge is not there, the blade actually is constrained kind of, okay, in some way. So, it will end up with lot of rolling moment. It will transfer all the moment to the helicopter, and as a consequence it will actually roll over on one side. When he provided these hinges, what happened, that the blade was now then free to move up and down, and as a consequence, I mean, people were able to fly with this design. So, by putting these hinges, so he put this flap hinge to enable this out of plane motion, lead lag hinge to enable this motion, and feathering hinge is anyway required because you have to change the pitch angle. All right. So, yeah.
Putting this flap hinge solved the problem of rolling over?
Yes, it did actually, yes.
So, the flap hinge will somehow change the aerodynamics, that is why?
It actually relaxes the blade. Okay. So, what is happening is, because of the increase in lift, blade would want to go up, okay, other side blade would want to go down. So, normally, you know, right, I mean, if you put a hinge anywhere, hinges cannot transfer moments, right, it allows free rotation. So, it will not transfer any moment. So, as a consequence, the moment which was getting transferred because of the cantilever kind of condition earlier, the rigid kind of condition earlier, got relaxed. So, the force transfer from the blade to the fuselage was less actually, and that is why this problem went away. But if you see, modern helicopters do not have the flapping hinge, because now, I mean, we have better understanding of everything, and so, but still when you give a particular input, the tip path plane actually tilts forward or backward. So, it still actually bends somewhat, and that bending is enough. So, these kind of small helicopters are capable of flying upside down. I mean, if you search on YouTube, okay, with the keyword of 3D flying of helicopters, you will find some amazing videos, okay, and you would not believe what you are seeing actually. All right. So, now we are going to focus specially on this particular motion, that is the flapping motion of the blade, okay, out of plane motion of the blade, called flap dynamics. So, we will look at each of these three motions individually one by one, so that we have slightly better understanding. The entire control of helicopter is actually achieved by this particular motion, flap motion. So, this flap dynamics is most important dynamics for any control design for a helicopter. Without incorporating this, you cannot actually model the helicopter motion or helicopter behavior at all. So, this is very important for us. So, this is a schematic of a possibly very simple model of a helicopter. In this, we are assuming that the rotor is like a rigid blade, okay, and it is supported by a hinge over here, okay. Exactly the way Juan La Cierva made his blades, okay. He put a hinge and the blade was free to flap about that axis, okay. So, it is very free. So, if you can imagine, I mean, if there is a hinge here, okay, if you do not have a stopper here, the blade will actually fall down and hit the ground, okay, because of the weight of the blade itself. So, normally all these articulated, so these kind of rotors which actually have this mechanical hinges are called articulated rotor hubs. So, in the previous diagram also there is this articulated rotor, okay. While the rotor which you are seeing over here, it is not articulated in flap, it has articulation in lead lag motion. It has a pin which enables the in plane motion, but there is no pin to support the out of plane motion, okay. So, it is, you can call it semi articulated, not fully articulated. And the bearing, so 2 flap hinges and 1 bearing makes it fully articulated. Then the other category of rotor hub is one which does not have any hinges, but it only has a bearing. So, such kind of hubs are called bearingless hubs, quite common, okay. So, I believe our ALH Dhruv, okay, our helicopter made by HAL Bangalore, that actually has this particular kind of hub. So, it has bearing, but it does not have mechanical hinges. Then the third kind is bearingless. So, it will not have any hinges and not even the bearing. So, instead of a mechanical bearing, they replace that with a torque tube and elastomers. So, instead of having a mechanical bearing, now you have elastomer. What is the elastomer? It is actually item which is made of polymer and metal. So, some kind of rubber and metal is a composite made with that, and you use shear between or slippage between different layers to enable rotation. So, it is supposed to be more advanced from the point of view, it does not require that much of maintenance, it requires less maintenance and it is more robust and so on. So, almost all modern helicopters, especially bigger helicopters, are now employing this kind of concept, okay. Alright, so that was about the hubs. So, now coming back to our this simple schematic. So, what we have here, we are just looking at one blade, and right now we are assuming that the blade has only one motion, that is the flapping motion, there is no other motion possible. So, blade can just move up and down, and for that we have provided a hinge and it is spinning with omega about an axis. So, we have also shown a flap deflection for the blade is rigid. So, there is no deformation in that, whole blade just moves up and down, and the symbol used for representing flap motion for blade is beta universally, okay. You cannot use any other symbol. So, whatever symbols I have shown are all symbols which are used by the community. You cannot suddenly start calling inflow by something else, okay, by omega or something, because omega is always reserved for rotation speed. So, all the symbols which I am showing are actually what you must use if you are writing a paper or you are doing any research in this area and so on, yeah. Because I have seen sometimes people, I mean, who, like, I go to a lot of presentations in electrical department, okay, people who are working on UAVs, quad rotors and so on, they end up calling roll angle with some other symbol, pitch angle with some other symbol, I mean, for aircraft roll, pitch and yaw angles by some random symbols. So, that is very confusing for me, because my mind is geared towards using a kind of symbols all along, because if I use some other symbols, people will actually not understand me. So, that is why it is very important. So, what are the forces which are acting on this particular blade? So, again we have taken a small infinitesimal segment, okay, like a blade element kind of thing, and we try to analyze what are the different forces which are acting. So, one force is of course the aerodynamic force, which is in terms of lift, it could be also drag, but then right now we are only looking vertical motion. So, we are only concerned about lift, drag is actually in the plane. So, when we look at the lag motion, we look at drag, right now we are not looking at drag, we are only looking at lift. Then because of the rotation itself, every point on the blade will experience significant amount of centrifugal force, and the centrifugal force is enormous. If you see in this, I have shown this aerodynamic force, centrifugal force and inertial force. I have not bothered to show the weight of the blade, right, but then definitely it is going to still act on the blade. But as you would see that the centrifugal force is several orders of magnitude more than the weight of the blade itself. Therefore, we never bother to look at that actually in our models. So, most of the helicopter models would never actually account for the blade weight itself. Helicopter weight, yes, that is important, but then blade weight is not considered at all ever. So, to set up the equation of motion for this blade, I must look at all the forces and account for those forces and corresponding moments because of those forces. So, what I have done here, I mean for each of the 3 components I have listed what is the corresponding force going to be. So, first is the aerodynamic moment, which, so to get the equation of motion, what I can do, I can ensure equilibrium of this blade about this particular axis, the hinge, and like I mentioned earlier, hinges do not transfer moments. So, effectively if I do a moment equilibrium, okay, or angular momentum balance, okay. So, that is like we have linear momentum balance which is force equilibrium, angular momentum balance which is moment equilibrium. So, if I try to ensure that moment equilibrium about this point, the moment because of aerodynamic force is given by this. So, I have this dfz which you saw earlier, vertical force multiplied with this distance. So, the distance of this element is y from the axis of rotation, same as before. So, this y, and because we are doing the equilibrium about this particular point, so it will be y minus e, that is the moment arm for this force. So, y minus e times dfz will give me the elemental moment because of this particular element, and if I go ahead and integrate it over the whole blade, it will come out to be like this. So, this part is aerodynamic moment. So, integration is going from e to r, y minus e times dfz, okay, vertical force, aerodynamic force multiplied with the corresponding momentum. Then we have moment because of centrifugal force. So, centrifugal force is acting in this direction, it is simply m omega square r, right, that is the value for centrifugal force. So, I look at the elemental mass which will be rho into your L, sorry, rho into dy, actually mass will be rho into dy, which is basically this rho is mass per unit length actually, okay, it is not the density of the material, rather in this case rho is actually mass per unit length. So, this rho multiplied by dy will give me mass, then you have omega square and y is the location. So, that gives me the centrifugal force. Now, the moment because of the centrifugal force, this is the arm, right, okay. So, that arm will actually be equal to y into beta, right, because this height divided by y will be equal to sine of beta, sorry, tan of beta. Beta is going to be again a small angle. So, we can approximate beta, tan beta with beta itself. So, therefore, I have y times beta coming in here, and that constitutes my centrifugal moment, fine. So, centrifugal force multiplied with the moment arm, force is m omega square r and m is basically dy into rho, and then remaining things are accordingly. So, that is the centrifugal moment, and then we have inertial moment. Now, my blade is actually moving up and down, and this beta is changing at every instance of time. So, I will have beta double dot, just like you have if a mass is if you look at a spring mass system, okay, my mass moves up and down. So, I have x double dot mx double dot as the inertial force. So, likewise we have rho L y square beta double dot y minus e square dy. So, that constitutes the moment because of inertial force. So, if I now add all these 3 together, I can actually end up getting my equation. In this I have even included the contribution from the weight of the blade, but then I will drop it out quickly, okay. So, the main 3 components are my inertial part, okay, beta double dot into something which is basically going to become flapping inertia. So, all of you are familiar with moment of inertia, right, for anything which is any mass. Normally, when we look at force, we look at force is mass into acceleration. When we look at your moment, it is your inertia, sorry, moment of inertia multiplied with the m theta double dot gives you the moment because of any particular thing which is undergoing rotation. So, inertia for rotation is moment of inertia, inertia for linear motion is your mass, right. So, that is my flapping moment of inertia. Here there is first moment of blade, but it will not come into picture because we are going to drop the term for corresponding to weight, because this is insignificant compared to all 3 other guys, it is fairly small. So, I am going to ignore that. So, my equation now, the leftover equation is now this I b, my flapping inertia, into beta double dot plus omega square into I b, which is again same thing, my moment of inertia multiplied by my flap angle beta, and that is equal to m beta. So, m beta is basically my aerodynamic flapping moment. We will see how also to calculate this m beta, but right now we will keep m beta as it is. So, this equation, I mean, does it look familiar to you? What is the kind of equation which we are seeing right now? It is a ODE or a PDE? ordinary differential equation or partial differential equation? It is ordinary, right. Okay. So, all of you can see it is ordinary differential equation of what order? Second order. Okay. All of you are from electrical, I mean, okay, you probably have seen this kind of equation for your LC oscillation circuits, right. People from mechanical know spring mass damper kind of systems. Right now, we have component for your mass, inertia, and a component for your stiffness or frequency. There is no term right now for damping, but you will see soon, okay, there will be a term for damping also coming into picture, but this is the basic equation. Okay, let us see what else next we have. Now, this equation right now is actually has derivative of time beta double dot. So, d2 beta by dt square. Now, normally for helicopter, okay, talking in terms of time, okay, this many seconds, this many microseconds, milliseconds does not make much sense to us. Why? Because everything we want to connect is to the rotation of the blade itself. So, what we will do is we will change the variable being used in this equation from dot to psi, that is from t to psi, because azimuth is more meaningful for me, because I can understand, I can visualize where my blade is right now. If you say where the blade is after 2 seconds, I do not know, but if you tell me my blade is at 90 degrees or 270 degrees, I understand where my blade is and what kind of forces it is experiencing. Okay. So, that is the change which we do now, and for that we define this new parameter beta star or beta double star. So, it is same as the dot, but now it is divided by omega. So, the transformation is done like this, d by dt into dt by d psi, okay, and d psi by dt you can see is actually omega, rate of change of your angle is your angular velocity. So, that gives me beta dot by psi now becomes beta star, and similarly by same analogy I can actually find out beta double star to be beta double dot by omega square. So, if I use these two things now in my original equation, I end up with a even more simplified version of the equation, which is beta double star plus beta equal to 1 by omega square I b into m beta, okay, and omega square is this omega is same as my rotational speed, I b is my moment of inertia. So, now this is a very simple equation, and by virtue of knowing second order equations you can see that this actually will have a natural frequency of 1, and this is a non-dimensional equation. So, we say 1 per rev because the whole equation has been divided by number of revolutions or rotational speed. So, normally we call it 1 per rev, which means my natural frequency is same as my rotational frequency. Okay. So, if my rotational frequency omega is 5 hertz, then my natural frequency is also 5 hertz, which is 1 per rev, that is 1 in one revolution, one time in one revolution, that is what it means 1 per rev, and the phase difference is actually pi by 2. So, you can imagine we are actually operating, okay, right now we do not know, okay, what is the nature of m beta, okay, depending on how this m beta is, we will see how the force response of this system is. Okay. So, this is just a regular equation which represents a forced vibration of a spring mass system or a LC circuit or something like that. All right. So, this is my flapping equation, this is a very simple equation right now you can see, and this is what actually is the key to the control of the helicopter. Okay. So, in this right now we do not know how to find out my aerodynamic flapping moment. So, let us look back at what was the definition for that. So, this m beta was y into dfz. Okay. So, dfz was my vertical force, and to get this, okay, we have to go back to the blade element theory formulation, right. We had written dfz was equal to nb into dl integral of that. So, if I go and do that, I will actually get that. So, going back to that equation, maybe I will just quickly go back there, okay, and we will come back here again, okay, right here, yes. So, we saw this, okay, this itself is my dfz basically, okay, or fz, and this is the non-dimensional form of that equation. So, there we are looking at the dimensional form, but finally we are actually interested in this, and we will convert everything to this kind of form. So, if I put my CL and sigma and everything, I will actually be able to find out CT as a function of theta or some other parameter, and which you see over here, okay, we will come back there, okay. Right. So, you see now theta has come into picture here. So, if I put everything back in that particular formula and evaluate, this is for the dimensional right now, we will make it non-dimensional in a moment. So, my m beta comes out to be half rho c is my chord, CL alpha is my lift curve slope, okay, which we saw earlier, r is my radius, omega is my rotational speed, and beyond that this theta is my pitch angle which my pilot is giving as an input to the helicopter. Okay. So, this is my pitch angle, lambda I is my induced velocity, right, which we could get by using momentum theory. And because now blade is also moving up and down, so there is a component of beta dot into y in up. So, I had perpendicular component of velocity, right, earlier, and in that we said okay, we will have a climb component because of the climbing of the helicopter if the helicopter is climbing, and we will have a component because of induced velocity because the rotor is inducing the velocity downwards. So, that was the main thing, but beyond that, because my blade is moving up and down like this, right. So, at any point I know if beta dot is my speed of this motion, flapping motion, beta dot into r is simply like v equal to omega r, that will give me a tangential velocity at every point, right. So, that is what is coming over here in form of beta star. Okay. So, by putting, so you see the Vp was actually Vi induced velocity plus y into beta dot, which I said. Okay. If I use this and ut is equal to omega y, using these two things in that original thing dfz, and of course, there is a y also multiplied here. So, you will end up with an expression like this for hover condition, and I can now rewrite my equation which was beta star star plus beta equal to 1 by omega square ib into mb in a new form, where I am now bringing in a new parameter called gamma, and mb I am using now mb m beta bar. So, there is a bar on top of that to differentiate from the previous m beta. So, what are these two things? I mean, it is the same thing as mb, but now it is sort of non dimensionalized. So, this m beta bar is now going to be non dimensional. So, now we define a new parameter gamma called log number, and it has a particular relevance. It is one of the key parameters which determines the behavior of the helicopter rotor. Okay. And it is defined as this particular thing. It is just ratio of your aerodynamic inertia by actual blade inertia. So, what is in aerodynamic inertia? It is, if you see, rho c CL alpha into r power 4. So, anything which has fourth power of length is actually an inertia term, you can imagine, right. I mean, if I want to say moment of inertia of a something which is say a beam, okay, normal beam, it is like ml 1 by 12 ml power 4 or something like that, it is there, right. Okay. So, that is how, so anything which has the power of 4 is actually moment of inertia term. So, this whole thing represents on the numerator represents moment of inertia of sort of air being displaced by the blade, you can imagine it like that, and at the bottom we have the inertia of the blade itself. The typical value this Lock number attains is between 5 and 12, okay, and m beta bar is then just the remaining thing, okay, divided by that particular parameter, all these parameters. Okay. So, now gamma is a non dimensional number and m beta bar is also a non dimensional moment. So, for hover, if I go ahead and do this entire integral and everything, okay, for a simple case it will actually come out to be like this. Okay. So, this was actually also on this side which has now been moved. So, this gamma m beta bar which we had this, so I am actually moving this part beta star by 4 on the right hand side of the, sorry. So, I have moved that gamma by 4 term which has beta star in that on the left side of the equation. So, now this equation looks more complete. Now, this is representative of a LCR circuit, okay, or for a spring mass damper kind of system. So, now you have actually something which is coming as a damping term. So, you have gamma by 8 into beta star. So, this gamma now you can see is directly influencing the amount of damping there in the rotor. Okay. It is quite interesting. Okay. So, if I have a rigid body, okay, if you apply a moment on that, it will actually just spin freely, right. But if I take the helicopter, if I apply a moment on this helicopter, you will see it will resist the rotation immediately. So, my rotor is spinning here, okay. If my rotor is spinning and if I give it a, I just give it a omega, okay, I just give it a small omega to make it spin, right. So, if it was a rigid body, it will, what will happen, it will keep on spinning continuously like this, right. But for a rotor with a blade spinning and everything, it will actually stop very quickly. So, this rotor itself, the entire rotor has tremendous amount of damping, it resists this rotation also, and that damping is showing up here in the form of Lock number. So, even for the blade, if my blade is spinning and if I tap the blade with a hammer or something, okay, it will immediately damp, it will come to its undisturbed orientation very fast. So, what is the amount of damping which is there? Of course, we can see here the natural frequency is 1, which we saw earlier, 1 per rev. So, here we normally put a nu beta square which is equal to 1, and the damping, if you compare the damping of this system with a spring mass damper kind of system, you typically have 2 zeta omega n equal to gamma by 8. If you assume the gamma to be equal to 1, gamma to be equal to 8, because it is typical value 5 and 12. So, if you take an average more or less, it will down to be 8, which is a typical number for lock number. So, for this number 8, I end up with zeta which is corresponding to 50% of damping. So, this is 1. So, you see zeta becomes 1 by 2. For a normal structure, okay, if I take a steel beam and give it a deflection, that has a damping of the order of 0.02, that is also high actually, it will be 0.002 actually, structural damping in such kind of system. For a hydraulic damper which is there in the door, which allows you to close the door on its own, that is of the order of 2%, okay, 1.5 or 2%. Here we have damping of the order of 50%. So, you can imagine it is like crazy enormous damping, very high damping. So, it is heavily damped, and so this entire formulation was done by assuming that the hinge offset was 0, that is why we have natural frequency equal to 1. If you assume that this hinge offset to be non-zero equal to some E, then my equation is modified slightly, and this term beta will actually have 1 plus E into S beta by I beta. Earlier this, if you put E equal to 0, it just becomes 1. So, the equation will be of a form like this, and then my nu beta square, which is my natural frequency, that is rotating flap frequency for uniform blade, would be given by nu beta square equal to 1 plus 3 E by 2 R. Okay. Again, this is only for rectangular blade. Otherwise, if the blade is not rectangular in nature, then we will use this S beta and we will calculate I beta, and from that ratio we will be able to get that. And there are more involved and complicated ways of calculating this also, but this formula gives you fairly good estimate. I can give you example, okay, for a big helicopter called Black Hawk. I believe you would have heard of this. There is a movie called Black Hawk Down. So, it is one of the main workhorses of US Army. My PhD research was actually on that particular helicopter. So, that has actually this hinge offset E equal to 6%. Okay. So, this E by R is actually 0.06. Do you have a calculator or phone or something? Can you just do a simple math for me? Any one of you? Okay, just calculate this. So, 3 by 2 into 0.06. So, first do that, 3 by 2, 1.5 into 0.06 and add 1 to that, and then take a square root of that. What are you getting? So, E by R, just replace that with 0.06. You will probably get 1.044. Okay. E by R we are using 0.06, and then find out what is nu beta. So, you have to do the square root of this whole thing. Hmm? 1.37. No, you have made a mistake. 1.044 would be probably the answer. 3 by 2 into 0.06 and then add 1 to that. Okay. Yeah. 1.04. 1.04, right? Okay. And that is actually the real first flap frequency of this Black Hawk helicopter. So, this simple formula, although it is very simple, it gives you fairly good estimate of the flapping dynamics of the helicopter. Okay, so that is one thing which we now know. Now, from here, okay, so this equation we have developed fine. Okay, we now also know okay how this whole thing looks like. So, if nu beta is not 1, then I will have a nu beta square over here. Okay, otherwise the equation remains the same. So, how does the response of this equation going to look like? Second order dynamics, right? Second order dynamics means, I mean, you would get an oscillatory response typically, right? And so there are various ways by which we can solve this equation. there is the simplest possible way by which normally people solve the equation is using what is called harmonic balance. So, we know that the solution of this flap angle beta is going to be of this form. So, there will be a steady part in that beta naught. So, this solution is periodic. So, what I can do is actually I can express this as a Fourier series. So, I can break this nice periodic solution into this Fourier series expansion beta naught plus beta nc cosine n psi and beta ns sin n psi, and the definition for beta naught and beta nc and beta ns are as per your Fourier series expansion term. So, beta naught is given by this, beta nc will be given by this, and beta ns is going to be given by this. Now, when we solve the flapping equation for a simple problem like the one that the kind of equation which we got here, if I want to solve for this kind of equation, I would actually assume that my beta, this series is adequately expressed by just using n equal to 1. So, I will assume that my beta is actually going to have beta naught plus beta 1 c cosine psi and beta 1 s sin psi. I will just assume them to have just one harmonic alone, and which is fine actually. Why? Because when I try to control my helicopter, the tilting of my rotor tip path plane is actually governed by this exactly this same thing. So, beta naught is actually my coning angle. Okay, my whole blade will actually deflect like this. Okay, it will create a cone, right. So, this is my coning angle. Then beta 1 c cosine psi, that is when my psi is 0, my cosine psi is 90 degrees rather, my cosine of 90 degrees is 1. So, when my blade is here, okay, or whatever my beta 1 c is, that will actually determine my tilting on the side. So, my blade may actually be like this. So, one part may go up and other may be down. What will that do? Actually, that will tilt my thrust vector to the side. Then my sine beta 1 s, when I am here, okay, that is 90 degrees, sorry other way around, okay, sine is 90 is 1, right, okay, sorry, my mistake, okay. So, other was actually, this one was actually sine. So, sine 90 is 1. So, my blade will actually deflect up in one side or deflect this way in the other side, okay. So, it will be, I mean, this may actually go down, this may go up like this, okay. So, this will be your lateral tilting. So, my thrust vector is tilted laterally. Other case, when the cosine is non-zero, it will actually, this may go down here and it may go up here. This will actually result in tilting of the helicopter forward. If you have to fly backwards, this will go down and this will go up actually. So, that is how actually your beta 1 c, beta 1 s and beta naught are actually coming out, and we will see how these are related to our pitch inputs also, because the pitch input also looks exactly the same way. My pitch input theta will actually have theta naught, which is my collective pitch input, theta 1 c, which is my cyclic input, one of the cyclic inputs, and theta 1 s. So, I will have theta 1 c into cosine psi and theta 1 s into sin psi, just like we have it for flap angles. So, to solve the equation, what we do is we just consider one harmonic and substitute everything back into the original flap equation, alright. So, that as I said, my theta, which is the pitch input given by the pilot, it will have a collective pitch input theta naught, theta 1 c and theta 1 s. So, theta 1 c is actually going to become or come into picture when your psi is 0 degree or 180 degrees, okay, then your this is non-zero. Theta 1 s is non-zero for 90 degrees and 270 degrees, but at every other azimuth location you have a combination of both these two, theta 1 c and theta 1 s, both of them will be present by some amount. So, this is the input coming from the pilot, and beyond that the blade itself may be twisted. Almost all helicopter rotor blades are twisted by some angle, not these small helicopters, these are actually toys. So, they do not actually go to twist the blade, because making a twisted blade is going to be more expensive compared to a straight blade always. So, as a consequence, these toy small helicopters do not have twisted blades. So, you may have actually some amount of twist. So, this is a geometric twist built into the blade itself, okay. So, if I use all this and put this back in my equation here, okay, and solve for everything, I would actually end up with flap expression for flap angle. So, what I have done actually, I put all these things in my equation on both sides. I will end up with harmonics on both the sides, right hand side and left hand side, and I will equate all the harmonics. So, you will end up with three equations which will give you beta naught, beta 1c and beta 1s. So, you see here beta naught we get explicitly, okay, nicely, beta 1c and beta 1s actually we get two linear equations. If I solve these linear equations, I will be actually able to get beta 1s and beta 1c, all this for a given control input. Let me close the door here. Okay. So, we can solve these two equations simultaneously and we can get beta 1c, beta 1s and so on. Okay.
They are not simultaneous, right?
They are wait, okay, in this case they are not, okay, fine, this is actually a simplified case about hover, so that is why it is not there. Otherwise, I mean for a forward flight case you actually end up getting a coupled equation, okay. I mean, but of course you can solve them and finally write a simple expression, okay. So, yes, you are right, okay. Yeah, I did not look at it carefully enough, and normally we get a simultaneous equation, okay. So, that is the case. Oh, there is a typo also here, I forgot to underscore here, so this did not go in. So, this is not beta 1c, it is actually beta 1c in the subscript, all right, okay. So, that was the flap dynamics, okay. And again I had to go through that in somewhat very compact manner, okay. I cannot actually go in the detailed derivation of everything, but it is very very important, and the key thing is that we have to understand how to solve this equation, okay. Effectively this equation, and there are various ways of solving these equations. I mean, I will come to that in a moment. Beyond that, any other question if anybody has?
While calculating the formula and beta, you have taken the distance y, and we are balancing from the hinge. So that should also be y minus a.
Yes, yes, fine. What you are saying is correct actually, but normally this e is very small. So very often we end up ignoring that. Okay. So in my formulas, I mean we have y minus e, wherever it is there, I will just put it as y. So if you are doing the integration numerically, then you can use e, there is no problem with that, okay. But if you are doing a hand calculation, it becomes simpler and convenient for us, because you see e is typically 4% to 6% for articulated helicopters, or it may be maximum 10%. So in that sense, I mean this e is fairly small number. So for simple calculations we ignore that, we just drop e compared to the overall distance, okay, which is much larger, okay. So but yes, otherwise I mean if you are doing numerical integration, we will definitely use e, okay. Okay. So now let us see lag dynamics. So again now we are only considering the lag motion for the blade, and we are not considering any other motion for the blade, and lag is basically my in plane motion. This motion is happening because of aerodynamic forces. So aerodynamic force which is present here is my drag force. In the flap motion, the aerodynamic force was my lift force basically, and again you will have centrifugal force because of the rotation of the blade, and because of lead lag motion. So lead lag is denoted by this symbol zeta, and so corresponding to the zeta motion, we also have the inertial force. So again, just like we did for the previous case for flap, we assume that the hinge is located here and hinge cannot transfer moment. So we will try to do a moment equilibrium about this particular hinge corresponding to each of the three forces. So I have written for aerodynamic moment. So now the aerodynamic force in this direction is dfx, earlier we had dfz, and the moment arm is y minus e. Then centrifugal moment here is, this is the mass, so it will be rho times dy, and we have zeta here into y minus e, y is the moment arm, okay. So that will give us the centrifugal moment, and there is inertial moment which is again, okay. So in this case I think rho into L is, because I mean this rho is actually it's slightly different unit than mass per unit length actually, that is why this small l has also come into picture. So inertial moment is also similarly zeta double dot into the corresponding mass, and the moment arm will be y minus e. So if you combine all that together, it is very similar to the way we derived for the flap equation, just that now I mean the motion is about lag. So we have aerodynamic, centrifugal and inertial moments. If we put everything together like this and simplify, we get up a very simple equation like this, which is exactly same as the equation which we saw for the flap equation also. We had beta double star plus nu beta square into beta equal to gamma m beta bar, right. That was the equation earlier, and now we have a equation like this here. The key difference is that the flap equation, the natural frequency was the flapping rotating flap frequency, now it is the rotating lead lag frequency. And another difference which arises because of this is the lead lag frequency is typically smaller for articulated rotors. For example, Black Hawk, I told you example, the flapping frequency which you calculated was 1.04. The lead lag frequency on the other direction is for the Black Hawk helicopter is 0.27, but then it is not necessary, it is always going to be less than flap frequency. For more modern rotors which do not have mechanical hinges, okay, bearingless kind of helicopters or hingeless kind of helicopters, lead lag frequency may be also slightly higher. So, this was the lag alone frequency, okay, or rather lag alone equation of motion. This is of less significance to us typically, okay. For control design, I mean the lead lag motion does not affect the overall dynamics so much, but then the coupling between flap and lag is of slightly more importance. So, here I have directly given you the equation, because again going through the derivation is we do not have enough time to go through all the things, but the reason why I put it here is because for a helicopter rotor the flap and the lag motion is continuously coupled, okay. And I have already given the reason, the coupling is coming through Coriolis force. Can anybody explain how this Coriolis force is coming into picture, how the flapping motion, this motion, okay. So, this motion, okay, and my other motion is this motion, okay. How these two are coupled, flap and lead lag. I am claiming that it is coupled through a Coriolis force. You are familiar with Coriolis force, all of you, I believe, right? Coriolis acceleration and Coriolis force, you are not? Okay. Yes, it is probably too much of mechanics for computer scientists. So, okay, then I have to probably go back a bit and tell you what is Coriolis force, okay, because otherwise you will not be able to appreciate this. Let me use the chalk and board little bit. I have too little room, maybe what I can do is I can exit my presentation and run OneNote, okay, then I can write on my screen and I can, so you are able to see that, okay. I will get back to the presentation in a moment, okay. Okay, so this is a disc, okay, and let us say it is spinning, okay. So, this is just like a merry-go-round, okay, you can which you find in your parks, okay, or in your fairs where you have these rides, right, which are things are going in circle. So, imagine this is a disc or a circle which is spinning with some angular velocity omega. Now, I can imagine, okay, some object, some body, a person, okay, so a kid is standing, for example, imagine a kid is standing on this merry-go-round. So, typically what force it is going to experience at this particular point, because of the rotation of this disc, centrifugal force, that all of you know, okay, this is going to experience the centrifugal force which will be in this direction, okay. Normally we denote acceleration, if you are looking at acceleration, then the acceleration is in this direction, which is called the centripetal acceleration, okay. The real thing is actually centripetal acceleration, the force is actually a pseudo force, okay, which we just put to balance for this acceleration. So, this is the acceleration, centrifugal acceleration, but now when it is stationary it is fine, but the moment this person starts to move, so it can either move this way or it can move the other way. So, the moment it starts to move with any velocity, okay, so I can call this maybe u and this guy as v, it will also start to experience what is called Coriolis acceleration, okay. The entire derivation for that, unfortunately I cannot do it right now, but it is given by expression like this, twice of omega cross v, this is the Coriolis acceleration component, okay, twice of omega cross v. So, effectively when this person, okay, let us look at this, if the guy starts to move in this, so we are saying omega, what is the direction of omega here, omega vector here, outwards, right, okay. If I have to show the omega vector for this, it is actually going to be omega into k. If I call these two, if I call this x and if I call this y, my z is out of plane of the board, okay, or out of plane of this, right. So, this is going to be my z. So, my omega here is what? It is given by say scalar omega into k hat vector, fine. This is my omega. Now, if I do omega cross v, now v I can resolve as u and v in x and y directions. So, my v here for this kid could be some u, I mean in this case I have shown minus u, I can make it plus u also. So, let it call. So, instead of this I can say this is going in this direction actually. I can erase this probably, okay, this is fine. So, u is in this direction and v could be again made positive. Right now I have shown it the way it may turn out to be negative. So, I have v in this direction, this is v and this is u, okay. Then I can write this as, right. So, right now what I am doing is actually mathematically I am doing everything, later on I will physically tell you what it actually means, okay, or how it is going to turn out. So, now let us do this omega cross v. So, omega k cross ui plus vj, right, and 2. So, this gives me k cross I is j, right, 2 u omega j and k cross j is minus I. So, it is minus 2 omega v. So, what has happened? The motion along x direction has resulted in a acceleration along y direction, right. I has become j, right. The motion velocity was in x axis, it is giving me acceleration in y axis, and here my motion was in y axis, it is become acceleration in x axis. So, this is what actually Coriolis does. So, in this case what we are seeing is, so I can even do just by using my hand, I can do my normal, okay, right hand thumb rule I can apply and I can find the direction in which my force is going to act or Coriolis acceleration is going to happen. So, omega and v. So, exactly same thing is happening for the blade also. So, my blade when it flaps up, what is happening, any point on the blade is actually moving inwards. It has a component of velocity which is directed towards the center of the circle, right. When my blade is, okay, moving up like this, okay, it is moving up and down, it is very difficult to imagine this blade actually moving up and down, okay, it is fairly rigid, but it actually does. So, when it is moving up, okay, any point on the blade is actually having a component which is similar to this u component, okay. So, this particular motion is going to result in a force in the in plane direction, okay. Similarly, now this motion is fairly easy, okay, lead lag motion, because there is a hinge. So, in this I can show you easily, okay, it is moving like this. This motion which is going to generate a tangential velocity which is like this v, right, and this velocity v is actually going to generate a force in normal direction, okay, flap direction, right. So, this is what the Coriolis acceleration is doing, it is actually coupling the flap and the lag motion of the. So, I will go back to the presentation mode. Unfortunately, I cannot enter the derivation of this whole how this whole thing comes, but I mean if you go and search about this is the Coriolis acceleration which actually causes tides in oceans and so on, okay, and it is responsible for many other interesting effects. Okay, so let us go back to the presentation. So, this is the Coriolis acceleration and the corresponding force, Coriolis force, which couples the flap motion and the lead lag motion. So, you saw the flap motion actually gives you velocity which is sort of out of plane, okay, which will give a in plane force, and the in plane force gives you out of plane force because of the Coriolis acceleration, that is in plane motion rather, okay, gives you the out of plane force. So, this is something which is definitely of significance and relevance for the overall dynamics, and the coupled flap lag equations are given by this form. So, exact same approach can be used for this to derive and come back to this kind of equation. Now, what has changed from the previous equation is that Earlier we only had beta star star plus nu beta square beta equal to gamma m beta bar. Now this new term has come into picture, which is coupling the lead lag motion with the flapping motion, and you can see this coupling is of skew symmetric in nature. So in one case you have 2 beta, other case you have minus 2 beta. Okay. So this effectively this does not affect the flap dynamics so much, but then this coupling affects the lead lag dynamics a lot. So it is of importance because sometimes your lead lag may become unstable and it may create problem for the rotor and so on. So this is the coupled equation. Okay. Eventually to have a more realistic model, we want to have model for all of these together. Okay. And at the end I will probably show you a coupled flap lag torsion model, okay, which will have all the 3 degrees of freedom coupled together, because they are actually coupled together. Now let us see what happens with the torsion dynamics. Okay. So lead lag dynamics we just looked very briefly, okay, because it is very similar, derivation and everything is very similar to your flap dynamics, and it is somewhat less relevant for us from the point of view of control. Torsion dynamics, it again has very important role to play. One is of course that your pitch input is coming in the torsion, right. Your pitch input is coming by changing the pitch angle of or feathering angle of the blade through your control input from source plate. So here again, okay, what we are doing, we are taking an element and we are looking at the forces which are acting on that. So you have centrifugal force and you have inertial forces, but now the dynamics is actually about this. So you have to look at this element and see how this element is going to pitch at any point of time. So you have, so if you divide this element as into 2 parts, so you have each of these points, okay, will have a center of gravity for the corresponding half, and as a consequence you will end up experiencing the centrifugal force. Now when this pitches up, okay, so this is the side view of the blade, you can see that this centrifugal force will actually end up generating a moment. Okay. This moment is called propeller moment, or this effect is also called a tennis racket effect. Any of you play tennis or badminton or any such game? It will probably be difficult to experience this in the badminton so much, because badminton rackets are fairly light, okay, and you do not actually move your wrist so much when you are playing, you are just hitting it straight. But if you play tennis, lawn tennis, okay, anybody played lawn tennis? You have played lawn tennis, then you would have definitely experienced this. When you try to hit the ball straight, you will experience that your wrist will automatically try to rotate, okay, and that happens because of the component of centrifugal force, because your hand is moving like this. So you have a centrifugal force component acting on the your racket. Okay. So therefore the name actually tennis racket effect, because it was observed by tennis players a lot. So when you try to move your racket like this, it will actually try to twist automatically, and it is also present in propellers, hence aerospace people call it propeller moment. Okay. So this is the propeller moment because of the component of the centrifugal force. Then you have inertial moment, and another thing is aerodynamic moment. So in the previous things we only saw aerodynamic forces, we did not look at aerodynamic moment, but any airfoil, any small airfoil section, when it is put under flow at different angles of attack, it will also have lift, drag, and a third thing which is called pitching moment. That is, whenever you try to generate lift, the airfoil will automatically try to resist that by generating a nose down pitching moment. It is more common for cambered airfoils. So airfoils which do not have symmetric section, I just draw it here. So normal, like the blade which you saw on this actually is a nice symmetric airfoil, that is its top and the bottom surface is identical. So this is approximately a nice symmetric airfoil, up surface or down surface, top and bottom, both of them are exactly symmetric. So this is symmetric about this axis. Okay. But when you go to a cambered airfoil, then the upper surface probably has more curvature, lower surface may have lesser curvature. So such airfoils, when you put them under flow, they will always generate a nose down pitching moment. Okay. So automatically the aerodynamic force will be such that you will try to pitch the airfoil down. This will not have so much of pitching moment initially, even at some smaller angles of attack it will not have so much of pitching moment, but at higher angles of attack even this symmetric airfoil will also have somewhat nose down pitching moment. But yes, this cambered airfoils or non-symmetric airfoils, they are always going to generate some amount of pitching moment, okay, and that is what is contributing towards this aerodynamic moment. So, you see this is so that is there, and beyond that also because of the offset between the aerodynamic center, shear center and your CG. Now, all these three terms probably would be alien to most of you. So, I will probably have to explain that also in some detail. Okay, so, right now these three things may be there, and beyond that, because there is a pitch link present, right, there is a pitch link which is trying to resist, it is of course, it is transferring the motion of the pilot stick input to the blade, but at the same time if the blade wants to move on its own, it is going to resist that, right. If I hold the this pitch link and try to move my blade, okay, it is going to resist that. So, it is going to act like a spring. So, that spring is accounted for here in terms of spring moment k theta into theta, okay, like a torsional spring. So, these are the different forces. I will come to this aerodynamic moment in the next slide some more. So, if I balance all these, I can actually develop the equation of motion for the torsional dynamics of the blade, and that equation comes out in a form like this, where If star is the feathering inertia. So, earlier we had inertia for bending, that is flap, inertia for lead lag, okay, which is similar to inertia for flap, okay, so they are almost same thing, especially for rectangular uniform blades. But this feathering inertia is a different kind of inertia, okay, and it is typically significantly small compared to your flap inertia or lead lag inertia. So, If star into theta double star plus nu theta square into theta. So, this is the equation of motion. So, you can see each of these three things have same second order dynamics, that is the flap motion, lead lag motion, torsion motion, all of them actually have same second order dynamics basically, okay. And just like we saw there was coupling between flap and lag because of Coriolis acceleration, now there is coupling between flap and torsion due to inertial and centrifugal terms. So, the centrifugal force as well as the inertial force is going to couple them if there is an offset between the pitch axis and the center of gravity. So, as you can see here, this is a typical airfoil section. Now, feathering axis is the axis about which the blade is pitching. So, the point about which you have put the bearing, that axis acts like the feathering axis or the pitch axis. Aerodynamic center is typically close to quarter chord for any airfoil. Okay. So, if airfoil is in subsonic flow, that is the flow speed is not comparable to the speed of sound, then my aerodynamic center is at 1/4 of the length of the chord. So, this is also kind of fixed, and third point is your center of gravity of the blade. Okay. So, this is something which you can choose to place wherever you want, or depending on the geometry it may be somewhere, okay, but it is definitely going to be closer to the leading edge than to the, because of the shape, right. The mass center will be somewhere closer to the leading edge than to the trailing edge, because more mass and more area is available over here. So, what happens when I look at the torsional dynamics, my feathering axis is this, that is the axis of rotation is this, aerodynamic force is going to act about this axis, okay, and my inertial force is going to act about this axis. So, as a consequence, actually not only the inertial force, but also the centrifugal force is going to act about this. So, if I go back, see this inertial moment as well as the centrifugal forces will have some components which will have this propeller moment. So, this propeller moment and inertial moment are all going to act about this CG point. So, as a consequence, if I look at the flapping motion and the pitching motion, they are also going to be coupled. So, this is now the coupled flap torsion equation. So, the flap equation is, these two terms were there beforehand, now the new terms have come up, which are now because of the feathering moment of inertia and your theta double star term, which is the inertia term, and theta, and the pitching equation which was earlier like this is now modified by inclusion of this again feathering inertia term, which is this, and this is the inertia coming because of the offset between the, so this is the offset xi between the feathering axis and the CG. So, this term actually brings in the coupling of the flap. So, this flap part actually gets contributed. So, this Ix star is because of that xi which we saw in the previous slide, and this is what you end up with, the coupled equation of motion. Okay. Now, each of these three dynamics have now been treated separately and also in pair to highlight that there is a coupling which is existing because of either the Coriolis acceleration or because of centrifugal, and also because of the location of the CG with respect to the feathering axis. And for all these three cases, we have assumed that the blade remains rigid. okay, and the motion is about a particular hinge. So, either a flapping hinge, a lead lag hinge or a torsion hinge, and that then brings us to the coupled flap lag torsion dynamics, okay, where each of these three things have been combined together, okay, and put together in one big form, okay, and you end up with an equation like this, which looks fairly intimidating, but then it is still a second order ordinary differential equation. It is nonlinear, it may be nonlinear because I mean this terms may actually, this m beta bar, m zeta bar and m theta bar, they may have actually terms corresponding to some of these parameters like beta, beta star or zeta or theta and so on. So, this equation may be nonlinear, but overall it is still a second order ordinary differential equation. So, solving such equations is not very difficult, and I am sure you are already familiar with many ways, but nevertheless I will talk about couple of ways by which we can solve this. One method we have already seen. What is that method to solve this equation? Newton-Raphson, no, we actually looked at a different method which we used to solve the flap equation. Right, yeah, I mean like harmonic balance, yes, okay, yes. So, harmonic balance. So, these equations can still be solved using harmonic balance. The problem with harmonic balance is that it will only give you steady state solution. It only tells me what is going to be the steady state after a disturbance has been applied, but as a control engineer we also need to know the intermediate things, okay, what is the response immediately after the disturbance is imposed. So, to get that we have to solve it in a different way, okay, and some of the ways will be discussed in tomorrow's class I believe, but today I will talk about some other methods. So, this you have already seen, harmonic balance. There is another method called finite element time, but this also is similar to this harmonic balance. It will also only give you the steady state solution, it will not give us the solution for transient, that is what happens immediately after I apply a disturbance, okay. So, then the third approach is basically your time integration, and time integration I mean there are many ways out there, many methods available. I mean you are familiar with probably Runge-Kutta, fourth order, fifth order, then you are if you are using MATLAB you already have this implemented in the form of ODE 45, right, okay, which will give you fourth order, fifth order, Runge-Kutta directly, okay. But all those are more cumbersome methods actually. What we use in dynamics community is what is called Newmark's algorithm. It is more common in structural dynamics, okay. People who work with structural dynamics who solve vibration problems, that is a very common methodology which is used for solving the flap equation or coupled flap lag torsion equations, and I will briefly tell you what it is actually and how it is used to solve the equation of motion. It is basically a finite difference based approach. There are many other finite difference based approach, and Runge-Kutta is also a finite difference kind of approach basically. So, this is here how it goes. So, our equation is a general second order equation which can be written in terms of mx double dot plus cx dot plus kx. So, m is your mass, so it could be a scalar equation with only one degree of freedom, or it could be a vector equation like the one which we saw here. So, this constitutes my mass matrix, this would constitute my damping matrix C, this would constitute my stiffness matrix K, because we always relate to the equation of the form. So, because we are mechanics people, okay, we do not look at LCR circuits, we are used to of looking at spring mass damper kind of system. So, we relate to everything to that, and we have, so this is my general equation of motion, okay. It could be linear, it could be non-linear. So, that is why I have said okay, my forcing may actually have terms corresponding to my states also, x dot and x double dot, it does not matter, okay, this method will still work perfectly fine. So, clearly this equation is valid for all time steps. So, we can write it down for a particular time step, say t n plus 1, okay. So, my equation then becomes m x double dot n plus 1 plus c x dot n plus 1 and so on, right. Now, Newmark, this is a guy, okay, who gave these two formulas, okay, and he said I can, so it's equivalent to a kind of Taylor series expansion. So, any function can be written in the form of Taylor series expansion and you can retain some terms, but it is not a usual Taylor series expansion. He has introduced now couple of terms which are unfortunately similar to what we have already used, beta and gamma, okay. So, this gamma is not our same as our lock number, okay. This is now Newmark's, this method is called Newmark's beta method. So, they have this beta and this another term gamma, this gamma is normally function of beta also. So, he gave these two formulas. So, he said I can represent my first derivative x dot n plus 1 as x dot n plus delta t times 1 minus gamma times x n double dot plus again gamma times x dot double dot n plus 1. Okay. So, this is one formula and the other formula is like this, which is for x n plus 1. So, you can imagine both of them are actually very similar to a Taylor series expansion, but with some factors which has been brought in, and this is now gamma and beta. So, typical values which we use for beta and gamma, I think gamma is half and beta is 1 by 4. Yes, that is true. Okay. So, beta is 1 by 4 and gamma is normally taken as half, okay. But then we may choose some other parameters also. So, what I do now using these two formulas, because this also represents the solution at a given time, I can plug them back into my original equation, okay, which is this. So, if I do that, if I put this guy x dot n plus 1 here, x n plus 1 here, what happens? I end up with the equation which is somewhat like this, and I can collect all the terms with x double dot n plus 1 on one side and everything else remaining is put on the right hand side. So, on left hand side now has only x double dot n plus 1, that is the acceleration term for n plus 1th time step, and on right hand side I have the forcing term and the remaining things which I already know. So, like the way we do in finite element finite difference ways, we start with a known solution or a guess solution at the beginning or solution at the time t equal to 0, use that solution to get the solution at the next time step, that is t plus delta t. So, from 0 we start, we go to delta t. So, we start from say n equal to 1, then we will go to n equal to 2, n equal to 3 and so on. So, every time we use the solution from the previous step. Now, when you do Runge-Kutta or something, you actually require information for 3 or 4 steps typically, okay. Only then you will be able to get the whole solution, but in this case the beauty is that you only need to know the solution from the previous time step, and that is all, and that is what we see. So, this whole equation now we actually at any instance of time. So, say if I am at time step 2, I already know the solution for time step 1, because either I start from some known condition or I start from some 0 condition. So, I know the conditions at the beginning. So, I know everything on this side except this guy. I do not know what is going to be my force at the next time step, which I am going to take now. So, what we do is if we say that if I our delta t, that is the gap between every step is very small, the change in my force is not very significant. So, I can approximate my f at n plus 1 with f at n. If I do that, then I know everything on this side, right. If I know everything on I will know entire right hand side, and if that is the case, then I can write this equation as a simple linear equation a x double dot n plus 1 equal to b n, which I can solve, invert the a or just use a linear solver to solve this equation, and I would actually be able to find out x double dot n plus 1. So, for a scalar I can do simply a by b, sorry, it should be b by a, okay, by mistake there is a typo, okay, it should be b by a, or if you are using MATLAB, okay, if I have to solve this in MATLAB, MATLAB has a built in linear solver called backslash operator, right, all of you know that. So, if you use backslash, if I do a backslash b, it will give me a linear equation solution. So, normally I would not have to do actually inverse of a into b, I do not have to write that, because of inverse of a is always more expensive to compute compared to solving the linear equation. So, I would simply in MATLAB I will simply do a backslash b and it will give me the linear equation solution. So, from that I get the acceleration. Once I know this guy, then I go back to my formulas, because in this is the only unknown part. So, I already know now x double dot n plus 1 what is my acceleration going to be at the next time step. Using that I can again calculate my velocity and also my displacement. Okay. So, I get my x dots and x dot n plus x n plus 1. So, effectively I get everything. So, is obtained again from the Newmark's formula. So, these two formulas are basically my Newmark's formula, and I would actually get everything, and I keep repeating this at every time step. Okay. So, that is why it is called marching in time. So, I start from time t equal to 0, take one step, take another step. So, you are taking steps. So, hence the term marching in time, okay. Or it is also called numerical integration in time and so on. So, at any point if I know the response at t n plus 1, I can get the response at n plus 1. Okay. So, normally when we start, this is the condition which we can employ, okay. That is, I can say at time t equal to 0 my flapping angle is 0, my velocity of the flapping angle is also 0, or sometimes I can actually use this for say if I have a I mean for the whole coupled flap like torsion, then I will have beta zeta and theta all equal to 0 and so on. Okay. So, all those things can be set to 0. Otherwise, if I already know some solution which is close to my starting point, I can use that as an initial thing. Okay. So, it is true about any ODE. Whenever we solve any ODE, we require some initial conditions, right. So, that is what it is actually. So, you supply the initial condition and the algorithm will give you the response immediately. Okay. I think that is all for today which I have covered. Okay. So, this method is very prevalent and we use it all the time in our flight dynamics models, okay, for solving the flap equation. But now I mean, okay, probably in the next lecture by Dr. Kothari, you are going to look at the Newton-Euler equation, that is the equation which represents the dynamics of any rigid body. So, such a equation you can never solve using this particular algorithm. Okay. So, you cannot use this Newmark's algorithm to solve that. To solve the rigid body dynamics equation, you only have to use something like your Runge-Kutta 4th order, 5th order. Okay. You cannot employ this particular method. The reason is again very mathematical, because of certain issues with the nature, the way the problem is set up, the sort of what is called stiffness of the problem. Okay. This kind of method is suitable only for solving these kind of equations, that is dynamics equations for blades, whether the blades are flexible or they are rigid. I mean, it is perfectly fine. Okay. You can still solve them using this, but you cannot solve the equation of motion for a rigid body using this particular approach. Okay. So, that is all. Okay. I think we still have couple of minutes. So, if you want to have any question, I can explain something in more detail.
So, why geometric twist is provided in the blade?
So, geometric twist is provided in most of the blades because it improves the performance in hover. Okay. So, one of the objectives of putting this twist is to make the inflow uniform. So, what happens, my blade is untwisted when the blade is straight, your inflow distribution, even though from momentum theory we see that it is actually uniform and constant, but in reality it is not uniform and constant. So, what happens, it actually becomes non-uniform and the distribution is actually somewhat like so inflow, if you look at the inflow distribution, it is somewhat like this bit. So, the inflow, okay. So, normal, first of all let me show you how the lift is distributed actually. Okay. So, typically for helicopter blade the lift is distributed like this. Okay. So, this will be your d of Ct by d of r, okay, and this is my r. So, this could be actually 1. So, from 0 to 1 my lift will actually distribute it like this for a helicopter blade. So, you can see the bulk of lift generation actually comes from between somewhat 70% to 95%. At the end it will actually go to 0. Why? Because there will be a tip vortex here, beyond this there is no blade, therefore, the lift has to come back to 0 here, okay, and it is somewhat like this. Now, the corresponding inflow is I think okay, sorry, okay. It is maybe I will just erase this and draw it again. So, inflow distribution is normally like this, okay. It will go to some finite value over here, okay. So, this is not uniform, okay. What we have assumed from momentum theory that the inflow is uniform and constant, but it is not uniform. To make this inflow uniform actually reduces your power consumption, okay, if you look at the power very carefully. So, the twist is given to make this inflow uniform, because what happens, your angle of attack alpha, okay, is actually theta minus phi, okay, and this phi is actually what is giving me this induced velocity, okay. So, this phi is going to change with r. So, this is actually a function of r, and if I want my airfoil, so all airfoils actually they will perform most optimally, they will have the highest lift to drag ratio if they operate at a particular angle of attack. So, for any airfoil, okay, what we call L by D, lift to drag ratio, because you want drag to be as low as possible and lift to be as high as possible. So, for any airfoil this will be a typical fixed number. So, if I want to ensure that my entire rotor blade operates at this particular L by D for the airfoil, then I should ensure that my everywhere my angle of attack is constant, and this angle of attack can be made constant if I change this also with this phi, okay, and that is why we give the twist. So, if I give this a twist, my theta will also be changed as a function of r, okay, and then I can ensure that theta minus phi is actually constant everywhere. Okay. So, if theta minus phi is constant everywhere, I have constant angle of attack, and I can choose this angle of attack to be the angle of attack which gives me best L by D. So, it is purely from the point of view of very good hover performance. So, if I want to make my helicopter more efficient in hover, I will give it some twist, and typical value of twist for helicopter blades is of 16 degrees to 18 degrees negative twist. Okay. So, this is a typical value for most helicopter blades, okay, or rotors. Okay.